Hi, this video is going to be on electron configuration, how the atom distributes electrons around the nucleus, creating a large volume for the atom, which is mostly empty space. In order to understand electron configuration, we have to look at the periodic table. It's the structure of the periodic table which helps us understand the distribution of electrons around the nucleus. Now, the first thing to note is that there are four sections to the periodic table. There's the S block in red, which are the first two columns on the left. That's the alkali earth, that's S2, and the alkalis, which are S1. Now, you have the D block, which is the transition elements. You have the P block, which is nonmetals and metalloids and a few metals. And then you have the F block, which contain a large number of radioactive elements, such as uranium. Now, it's very important to note that you have two columns for S, 10 columns for D, 6 for P, and 14 for F. Now that's going to be very important. Now, each level, each sublevel, for instance S, contains one orbital. Now an orbital is a sphere that can contain two electrons. This is right from the chapter, the lecture. One spins in one direction, the other spins in the other direction. That's an orbital. I can put two electrons in each orbital. So S has two columns, so you're going to have two electrons, so there's going to be one orbital for the S section. P, you have six columns. I'm going to have six electrons, two per orbital, so I'll have three orbitals for P. D has 10 columns, so it'll be 10 electrons, so there'll be 5 orbitals, and F will be 14 electrons and 7 orbitals. Okay, so that's the first thing you want to see is the nature of the periodic table. It's broken into four sections, S, P, D, and F. Next, we want to look at the suborbital capacity, and I think we already talked about it. S has a capacity of 2, it's 2 columns, capacity of 2, 1 orbital. P has a capacity of 6, 6 columns, so there's 3 of those little orbitals. D has 10 columns, capacity of 10, 5 orbitals. F, capacity of 14, 14 columns, 7 little orbitals. That's going to be important information for you to be able to do the electron configuration. You get it? So far, so good? That's all you have to understand right now, nothing else. The suborbital capacities. Now, where do we see the suborbitals for the first time? Well, you have principal quantum number. We'll get into what that might mean a little bit later. We just call it small n. Okay. The first level, you see just the s suborbital. When you say principal quantum number, or when I say principal quantum number, I mean the first level, the first shell, let's say, just has a suborbital of s. The second shell has a suborbital structure of s and p. The third shell has a suborbital structure of spd. I have to change the timing on this a little bit. And the fourth shell has a suborbital structure of spdf. Now, so the first time you see an s is in the first shell. So that would be 1s, then 2s, then 3s, then 4s, etc. It's very important. Sounds a little crazy, but trust me when I tell you, it's very important. The first time you see a p suborbital is in the second shell, so that would be 2p. The first time you see a d, so in the d section, the very first d suborbital will be 3d. The first time you see an f is in the fourth shell, so the first f is going to be 4f. So when we go back and we look at the periodic table in the 4 sections, we're going to know where we have 3D, 4D, 5D, 1S, 2S, 3S, 2P, 3P, 4P, 4F, and 5F, etc. So it'll make a lot more sense. Now, I'm not asking you to write electron configurations yet. I'm just asking you to understand what we've talked about so far. We've talked about the 4 sections of the periodic table, SPDF. We looked at the capacity. Where do you see the suborbitals for the first time? And that's really it. So let's develop this slowly over the next half an hour and see if you can't understand a little bit more every slide. Now, here we have the suborbital capacity for S is 2. Where do you see suborbitals for the first time? You see the S in 1. So the first column is going to be 1s. What's that little 1, the superscript? That's the number of electrons that are in it. So the first element, hydrogen, would be 1s1. Okay, 1s1. So every period going down, the first one would be 1s, then 2s, then 3s, and I'll let this run, and it goes on down to 7s. I'll let that run. Let you look at that. So francium, for instance, would be 7s, 7s1, because that's going to be the last element on the left there, next to the 7. P is going to be something similar. Now, the first time you see a P is in the second level, and that's what it says there. The capacity is 6 columns. The first time you see the P is in the 2. So the upper left square, that's going to be 2P. So that'll be 2. Then underneath that'll be 3, 4, 5, 6, 7P. So that's how you number the P's. And that's why you number the P's in that fashion. So it'll be 2, 3, coming up on it, 4, etc. I'll let that run for a minute. And then 7P. Now, the next section is going to be D, and the suborbital is D. The capacity is 10. The first time you see it is in 3. So the very first D would be 3D. So the first row is 3D, then 4D, 5D, 6D. Again, the superscripts, you may have figured out by now, is going to be, the superscript is going to be the number of electron that is in that particular suborbital. So as you go across, there's 10 columns, so it'll be D1 to D10. So that's 3D, 4D, 5D, and then it'll be 6D. I'll let that run for a second. There we go, then 6D. Now, here we have F. F is going to be the exact same thing. You're going to have the suborbital F has a capacity of 14. The first time you see an F is in the fourth shell. So you can see the F's are 14. They're going to be under it. Glenn Seaborg won the Nobel Prize for developing this type of periodic table years ago, before the World War II, before the 1940s. You had this group of elements in with the transition elements. So they're called intertransitional, some people say. So anyway, you'd have, that's 4F, because the first time you see it is in 4, and then 5F, etc. Now, putting it all together, we'll spend some time on this, that's how you have it. So you have 1s, 2s, 3s to 7, and then P, and then D, and then F. So that's how they're numbered. That's how they're numbered. So you say to yourself, well, you're going from 4s to 3D. Does that make sense? Well, okay, it doesn't make sense from one point of view, but it makes sense from another point of view, in that is that the first time you see a D is in the third level. So it makes sense to go from 4s to 3D to 4P to 5s to 4D to 5s to 6s, etc. Okay, now, what we're going to do now is we're going to number them. This is how you number the periodic table. So this is how the order of filling is going to take place. The filling is going to take place according to how the periodic table is numbered. Right? Sounds simple. So you go from 38 to 39. You go from 20 to 21. So you go from 4s2 to 3d1. That's how it's numbered. Now look at 56. You're not going to go to 5d1 because that's not how the periodic table is numbered. You're going to go from 56 down to 4f1, and that'll be 57, and then it will pick up from there. So you have to watch and see how the periodic table is numbered. It's very, very, very important. So you're not going to go from 56, it just makes too much sense possibly, but so you're going to go there. You see that? So 56 there, then 57 there, then you go back up to 5D. There we go. And then over to 6P, and then 7S, and then 5F. See, now you're going to go back down to 5F. All right? So, very, very simple stuff. Okay, watch what you're going to do. Watch what you're going to do. Okay, you're going to go down to, from 88 and 89 is going to be 5F1. 5F1 will be 89. There we go. And that'll go out to 102. And then 103 will be up at 6D1. See how that goes? Now I also filled in, I stopped it again here because I'm filling in. These are all, newly discovered elements, and I'm going to number them all the way across because some of the elements are being discovered as we speak. They only have one element in the 7P section, but there are actually two or three elements that are filled in there. So I'm going to fill them all in because they will find them shortly. And by the time I retire, they may even extend it farther to 8S for all we know. So I'm going to continue filling from 7P1 to 7P6. And again, they may find additional elements, 119 for instance. Now what we're going to look at, again on the filling, we're going to look at I'm going to put arrows in and how it fills across. And you don't really need to know elements when you're first doing this. You simply have to have a blank periodic table. There's really no need for putting elements in at this point. We're trying to see how it's organized relative to electron filling. So you go across to 1s1, 1s1 to 1s2 to 2s2 to 2p6 to 3s2. Okay, you see how it's going? And then it's going to go to 3p6. So watch this carefully. I will go away, let this run for a little while, and I'll be back. Okay, so now it's going to go 6D and then 7P, and that will end it. And now we'll start something else relative to how these things fill. Hold on. So you saw that I went from 1S2 to 2S2 to 2P6, 3S2, 3P6, 4S2, and then it was 3D10, and then 4P6, 5S2, 4D10, 5P6, 4S2, and then down to 4F14, up to 5D10, 6P6, 7S2, down to 4F14, and then up to 6D10, and then 7P6. And what I'm going to do is I'm going to go through another quick exercise where you can see a reaffirmation of this filling, this order of filling. Okay, here we have we're going to look at the order of filling again, going from 1S2 all the way over to 7P6, okay, and there's the 2S2 and then 2P6, etc. I'll let this run, I'll let you take notes and examine it, make sure you can follow it, and then we're going to do some examples. Okay, do you get it? I hope so. Now what we're going to do is we're going to do some examples. For instance, what is the long form electron configuration for Z equals 7? So Z is, remember what Z is? Z is the atomic number. So that'll be nitrogen. But we really don't care about the type of element it is. We only care about the Z. You know, where is it on the periodic table? Then once we can do electron configurations and something else after this, then we can actually graduate and actually look at what is the name of an element and what are some of its properties relative to chapter 6, etc. So let's look at this this worksheet, and let's see if we can do the long form electron configuration for each element listed in terms of Z. Okay, so Z would be 1s2. Now look at your periodic table. That you're going to have that out. That's going to be very important. And what I'm going to do is I'm going to let this run, and this will take a while. And I'm going to let this run. Now remember 28. Remember how we numbered the periodic table? 28 will be the the element 28. So whatever element that's going to be, but it's the way the periodic table is numbered, and that's going to be how it's going to look. Okay? All right. Okay, this is 52. And then the next worksheet or chart is going to be the same thing, but just bigger, bigger Z's. All right. So that's going to be it. Okay. So those are the electron configurations for each of those. This is going to be simply 68 to 103. Same idea, but I'm going to go through this a little bit more quickly. I'm going to only put in 2 seconds per slide and see if you can keep up. Or put it on hold and see if you can answer the questions before I do. Okay, here's number 68, 1s2, 2s2, etc. I'm going to be back near the end of 103. Remember to put it on pause and see if you can do it yourself. These will simply be the quizzes that you're going to get. You're going to have to know how to do each one of these, or any type of anything on the periodic table you're going to have to be able to do. Okay, the last one, 103, I'm going to reduce it to 1 second per slide. 1 second per slide, 103. See if you can keep up. Short form electron configuration is exactly what it says. It's a shorter way of doing what we just did, which is called long form electron configuration. In the short form electron configuration, you're only doing essentially the final period. So if you have something like sodium, which is number 11, and that's 3s1, you would put as the first item, you would put neon in brackets, and then you would put 3s1, because you're just doing the last period of the electron configuration, because that's going to become very significant when we talk about bonding. We're going to look at the last period of the electron configuration when we look at bonding. So let's look at some very simple rules to help us understand how to do short form electron configuration. First thing you do is you're going to write the symbol for the preceding noble gas in brackets. So whatever that symbol is, let's say it's sodium, for instance, then the preceding noble gas will be neon, and that'll take care of 10 electrons. This will satisfy the number of electrons equal to the atomic number of the preceding noble gas. And then you start writing the rest of the electron configuration. So for sodium, it would be 3s1. So The neon would take care of 10 electrons. You have 1 electron left because it's in the 3s1 area, because sodium has 11 electrons, neon has 10, so there's 1 left over. And 3s1 would be the finish of the short form electron configuration. Now let's look at some practice problems that you can try on your own. And as I uncover them, try to do them yourself. See if you can pause the movie, work on them, and then check your answers. I'm going to start it off slowly, where you'll have 4 seconds between slides, and then I'll speed it up to 1 second a slide. Don't forget that you can put it on pause to check your work. Let's begin. So here's nitrogen, and nitrogen is going to be helium, will be the preceding noble gas, and then that takes care of 2 electrons, and then you're in the 2s2 position, and then 2p3, and that finishes it. We'll do one more slowly, and then we'll speed things up, so it'll be 1 second per slide. Okay, number 28. That's good. Now we're going to start off and be a little bit more quick, a little bit quicker. Okay, the next batch, we're going to go 4 seconds, back to 4 seconds. So 68, if you look where that is on the periodic table, then you're going to go to xenon, and then 6s2, and then 4f12, and then 74, 6s2, 4f14, and then 5d4. Now we're going to pick it up, and it's going to go, but more quickly. Okay, now we're going to look at what is the final orbital suborbital electron configuration. In other words, if I'm doing electron configuration, what is the final entry in that long, drawn-out electron configuration? And this is going to be the most important one. This is the one that will really give you a lot of information relative to bonding. So let's look at the final orbital suborbital. Let's see if we can look at that. That's going to be very important for things that we're going to do. How do you do what I call final orbital suborbital electron configuration? How do you do that? So let's look at some very basic rules involved in identifying it. And then we'll do some practice, and then we're done. We're done the lecture. And at the end of this lecture, you should be able to do things pretty quickly. Okay. So you want to write the final what? Let's change the timing on this because it's a little bit too dramatic. So you want to write the final energy level suborbital electron exponent for the electron configuration of an element. So what does that mean? Let's look at that again. You want to write the final energy level suborbital electron exponent for the electron configuration of an element. So let's look at A. That's the first one. So A is, we know that it's hydrogen, but it's going to be 1s1. C, look at where C is. C would be 3s2. Look at where Q is. Q would be 2, 3, 4, 5, 6, 7p3. Okay, are you ready? Do you think you're ready? So what we'll do is we'll go very slowly at first, and then we'll get much more rapid. So the first one is 1s2, and then B, I'm sorry, 1s1, and then B is in the 1s2 position. Okay, and then C is going to be in the 3s2 position. So we're going to take our time with this first one, see if you can get it. All you need to write is the final energy level suborbital electron exponent. Okay, C. What is C going to be? Let's change the timing on this because the drama is just unbelievable. So, where are we? C. That's obviously 3s2. And then we're going to go to 2p4. And now we're going to let this play more quickly as we get a little bit more used to this. Then 4s1, and then 3d3, 3d5, 3d10, etc. Now we're going to go very rapidly through this. Okay? Hope you enjoyed it. See if you can do these yourself. Put it on pause. And our quizzes that we're going to have are going to demonstrate your ability to do these exact same problems. Have a nice day.